March 15, 1870. Manchester, England. The engineering assessment from British excavation specialists would never fully capture what they discovered in the muddy construction sites that bitter spring morning. American steam shovels, operating with mechanical systems that contradicted everything European precision engineering claimed, was necessary for reliable earth-moving equipment. Through the hissing steam and grinding gears of the English countryside, identical Marion and Bucyrus machines moved tons of earth with consistency that European multi-cylinder excavators could not match. No sophisticated governors, no precision linkages, no complex multi-part assemblies, yet they excavated with reliability that European advanced systems could not sustain. In European factories, master engineers required intricate multi-cylinder steam engines to achieve proper excavation control. Each machine incorporated sophisticated precision mechanisms, complex governors, advanced linkages, elaborate steel assemblies. Most carried performance specifications only perfect conditions could support. The Americans were operating with engineering philosophy the Europeans had dismissed as primitive: single-cylinder engines, basic cable systems, cast iron construction, design principles that prioritize durability over sophistication. 4,000 miles from European workshops, the most decisive construction revolution in industrial history was proving itself, not in advanced complexity, not in precision mechanisms, but in the mechanical simplicity that kept American machines running when European sophistication failed completely. The expiration of William Smith Otis's steam shovel patents on January 1st, 1870, unleashed a torrent of American engineering ambition that had been bottled up for 3 decades. Otis, the brilliant 22-year-old civil engineer who had invented the steam shovel in 1835, died of typhoid fever just months after receiving his patent in 1839. His family had jealously guarded those patents for nearly 40 years, creating a monopoly that stifled innovation and left American earth-moving technology frozen in time. But when those legal restrictions finally dissolved, railroad companies across the continent faced an unprecedented challenge: moving millions of cubic yards of earth across thousands of miles of hostile terrain. The scale of American railroad expansion in 1870 dwarfed anything Europe had attempted. The Transcontinental Railroad had been completed just 1 year earlier, but dozens of branch lines, spur tracks, and regional connections demanded massive earth-moving operations through mountains, across prairies, and over rivers. Manual labor alone could not meet the demand. Armies of Irish and Chinese workers had carved the first transcontinental route, but the sheer volume of earth that needed moving for the next phase of American expansion required mechanical solutions. European manufacturers sensed opportunity in America's infrastructure boom and arrived with confidence bordering on arrogance. Their excavators represented the pinnacle of precision engineering: sophisticated multi-cylinder steam engines that delivered smooth, controlled power through complex governor systems. Intricate linkage assemblies translated steam pressure into precise digging motions, while elaborate gear trains provided variable speed control that manual operators could adjust for different soil conditions. The European machines featured advanced steel construction with carefully machined joints and precisely calibrated components that worked together like mechanical symphonies. British engineers from companies like Rust and Proctor pointed to their machines' ability to excavate delicate trenches for gas lines and water mains in London's crowded streets. German manufacturers like Menck and Hambrock demonstrated how their multi-cylinder engines could maintain consistent power output regardless of load variations. French designers showcased linkage systems so sophisticated they could literally sculpt earthworks with architectural precision. These were not crude digging machines, but precision instruments that transformed excavation from brute force labor into refined mechanical art. When the first American-built Marion and Bucyrus steam shovels rolled off production lines in Ohio, European engineers could barely contain their dismissive laughter. Henry Barnhart's Marion designs featured single-cylinder steam engines that seemed almost primitive compared to European multi-cylinder sophistication. Instead of complex linkage systems, American machines relied on basic cable and pulley arrangements that looked like something a blacksmith might devise in his spare time. Where European machines showcased precision-machined steel components, American designs embraced heavy cast-iron construction that appeared crude and utilitarian. The philosophical divide ran deeper than mere mechanical differences. European engineering culture prized theoretical sophistication and precision manufacturing that demonstrated mastery over complex technical challenges. Their steam shovels were engineering statements as much as working machines, designed to showcase the advanced technical capabilities of European industrial civilization. Every component was crafted to exact specifications, every system optimized for maximum efficiency under ideal operating conditions. American manufacturers approached the problem from an entirely different direction. Barnhart, the frustrated shovel operator turned inventor, had spent years watching sophisticated machines break down under harsh field conditions. His design philosophy prioritized mechanical reliability over theoretical elegance. Single-cylinder engines had fewer moving parts that could fail. Cable systems were simple enough that any railroad mechanic could repair them with basic tools. Cast-iron construction could withstand impacts and temperature fluctuations that cracked precision steel assemblies. The contrast became evident during the first major field tests in 1871. European machines initially outperformed their American counterparts in controlled demonstrations, excavating with precision and speed that impressed railroad engineers. Multi-cylinder engines provided smooth power delivery that translated into consistent digging rates. Sophisticated governor systems maintained optimal steam pressure regardless of load variations. Precision linkages allowed operators to position buckets within inches of specified locations. But American railroad construction presented challenges that European designers had never encountered. Midwest prairie soil froze solid in winter and turned into adhesive mud during spring thaws. Mountain construction exposed machines to temperature swings from below freezing to over 100 degrees Fahrenheit in the same week. Desert conditions filled precision mechanisms with abrasive dust that wore away carefully machined surfaces. Most critically, American job sites operated hundreds of miles from the nearest machine shop, making complex repairs impossible. The brutal winter of 1874 provided the first decisive test. European excavators, with their sophisticated multi-cylinder engines and precision mechanisms, began suffering catastrophic failures as temperatures plummeted. Complex governor systems froze solid when moisture in steam lines turned to ice. Multi-part engine blocks cracked when thermal expansion exceeded the tolerances of precision machine joints. Intricate linkage assemblies seized when dirt and moisture froze in carefully calibrated bearing surfaces. Meanwhile, Barnhart's supposedly primitive Marion shovels continued operating through the harsh conditions. Single-cylinder engines generated enough heat to prevent freezing and had fewer precision surfaces that could bind with ice. Basic cable systems remained flexible even in extreme cold because they relied on mechanical advantage rather than precision fit. Cast iron construction expanded and contracted with temperature changes without cracking because the material itself was more forgiving than precision steel assemblies. By spring of 1875, American railroad companies were quietly canceling orders for European equipment and placing new contracts with Marion, Bucyrus, and other Ohio manufacturers. The sophisticated European machines sat idle in repair yards, waiting for replacement parts that had to be shipped across the Atlantic and custom fitted by trained technicians. American steam shovels, dismissed as crude farmer engineering just months earlier, were moving earth at unprecedented rates across the expanding American rail network. The Marion Steam Shovel Company's rail-mounted excavators transformed American railroad construction through a deceptively simple innovation that European designers had overlooked: standard gauge mobility. Henry Barnhart's machines rode on the same 4'8" and 1/2" track gauge that carried freight trains across the continent, allowing steam shovels to travel directly to work sites under their own power. Instead of requiring specialized transport equipment and complex setup procedures, Marion shovels simply steamed down existing rail lines, positioned themselves at excavation sites, and began digging within hours of arrival. This mobility advantage compounded rapidly across large construction projects. The Chicago and Northwestern Railroad's expansion through Wisconsin in 1876 demonstrated the strategic value of Barnhart's approach. Marion shovels moved along the construction route as work progressed, excavating cuts through hills, digging foundations for bridges, and clearing roadbeds without the lengthy setup and teardown cycles that plagued stationary European machines. Railroad superintendents discovered they could deploy Marion equipment like mobile artillery, concentrating digging power wherever the work demanded maximum effort. The mechanical systems that European engineers had dismissed as primitive proved remarkably well suited to this mobile operation. Single-cylinder steam engines started quickly and required minimal warm-up time, allowing crews to begin excavation within minutes of reaching a work site. Basic cable and pulley systems transmitted power efficiently without the complex adjustments needed for European multi-cylinder engines. Most importantly, the robust cast iron construction withstood the constant vibration and impact of traveling over rough railroad tracks that would have loosened precision assemblies in European machines. Barnhart's engineering philosophy emerged from his years as a shovel operator, who understood that theoretical sophistication meant nothing if machines could not operate reliably in harsh field conditions. His patent applications from 1883 revealed his focus on mechanical failure points that plagued existing equipment. Where competitors used simple chains to support shovel booms, Barnhart designed solid iron rods called hog rings that distributed stress more evenly across boom assemblies. His bucket designs incorporated heavier gauge steel and reinforced attachment points that resisted the repeated stress cycles of constant digging operations. The reliability advantage became most apparent during extended construction campaigns. The Union Pacific Railroad's branch line construction through Nebraska in 1877 required moving over 2 million cubic yards of earth across 300 miles of prairie. European excavators initially maintained their performance advantage in ideal conditions, but their sophisticated systems began deteriorating under the relentless daily grind. Multi-cylinder engines required frequent adjustment as wear accumulated in precision governor mechanisms. Complex linkage systems developed play in bearing surfaces that reduced excavation accuracy and increased operator fatigue. Marion shovels, by contrast, improved with use as their cast iron components wore into optimal fit. Single-cylinder engines operated with consistent power output because they had fewer precision surfaces that could deteriorate. Cable systems actually became smoother as new cables stretched and settled into their pulleys. Railroad construction crews began requesting Marion equipment specifically because they could predict consistent performance week after week without unexpected breakdowns that halted entire construction operations. The harsh winter of 1875 provided the most decisive demonstration of American design superiority. European manufacturers had promoted their sophisticated steam governor systems as providing superior power control in varying conditions, but these same precision mechanisms proved catastrophically vulnerable to extreme weather. Multi-cylinder engines with complex internal passages allowed moisture to accumulate in areas where it could freeze and block steam flow. Precision machine governor weights seized when ice formed in their bearing surfaces, causing engines to lose power regulation just when consistent performance was most critical. Barnhart's supposedly crude single-cylinder engines demonstrated remarkable cold weather reliability because their simpler internal geometry prevented moisture accumulation and their larger thermal mass resisted freezing. The single cylinder generated enough heat to keep steam passages clear even in sub-zero temperatures. Basic cable systems remained functional in extreme cold because they relied on mechanical advantage rather than precision tolerances that could bind with ice formation. European engineers struggled to comprehend how their theoretically superior machines could fail so completely, while American designs continued operating. German manufacturer Menck and Hambrock dispatched technical representatives to investigate the failures, expecting to find operator error or maintenance deficiencies. Instead, they discovered that American operating conditions exceeded the environmental parameters that European machines had been designed to handle. Prairie construction sites experienced temperature swings of over 100 degrees Fahrenheit between summer and winter extremes. Dust infiltration during dry seasons filled precision mechanisms with abrasive particles that wore away carefully machined surfaces. The psychological impact on European manufacturers proved as devastating as the mechanical failures. Companies that had built their reputations on engineering sophistication found their most advanced designs outperformed by machines they had dismissed as crude farmer engineering. British firm Ruston Proctor, which had promoted its multi-cylinder excavators as representing the pinnacle of steam shovel technology, quietly withdrew from American markets after experiencing catastrophic warranty claims during the winter of 1875. American railroad companies, initially skeptical of domestic manufacturers, began placing increasingly large orders with Marion, Bucyrus, and other Ohio companies. The Pennsylvania Railroad's locomotive superintendent wrote in his 1876 annual report that American steam shovels had reduced earth-moving costs by 40% compared to manual labor, while maintaining excavation schedules that European machines could not match due to reliability problems. The Baltimore and Ohio Railroad canceled outstanding orders for European equipment and standardized on Marion shovels after experiencing consistent performance through 2 complete construction seasons. By 1878, Marion Steam Shovel Company had established itself as the dominant American manufacturer, with Bucyrus and other Ohio companies capturing the remaining market share. European manufacturers found themselves relegated to specialized applications where their precision capabilities provided genuine advantages, such as urban construction projects with access to sophisticated repair facilities. The vast American railroad construction market, which represented the largest earth-moving opportunity in industrial history, belonged to companies that had chosen reliability over sophistication. The transformation reflected a fundamental shift in engineering philosophy that would define American industrial development for the next century. Theoretical elegance yielded to practical effectiveness. Precision manufacturing gave way to robust construction that could withstand harsh operating conditions. Most importantly, American manufacturers learned that market success depended not on impressing engineers with sophisticated designs, but on providing tools that allowed working crews to accomplish their jobs efficiently and reliably, day after day, year after year. The success of Marion's rail-mounted steam shovels triggered an explosion of American manufacturing that transformed Ohio into the steam shovel capital of the world. Edward Huber, the prolific inventor who had revolutionized agriculture with innovations like the revolving hay rake, recognized the strategic opportunity and established Marion Steam Shovel Company as a formal enterprise in 1878. His financial backing and institutional credibility provided the foundation for Henry Barnhart's mechanical innovations to compete against established European manufacturers, who still commanded respect in engineering circles despite their field failures. Bucyrus Steam Shovel and Dredge Company, founded in Bucyrus, Ohio in 1880, embraced the same engineering philosophy that had made Marion successful. Their designers studied Barnhart's patents and developed complementary innovations that reinforced the American approach to steam shovel construction. Where Marion had perfected single-cylinder steam engines, Bucyrus engineers developed improved boiler designs that generated steam more efficiently while maintaining the robust construction that allowed reliable operation in harsh conditions. Their bucket assemblies incorporated even heavier reinforcement than Marion designs, using quarter-inch steel plate where competitors relied on lighter-gauge materials. The Osgood Company of Troy, New York, entered steam shovel manufacturing in 1882 with designs that pushed American engineering philosophy to its logical conclusion. Their machines featured cast-iron construction so robust that field crews nicknamed them indestructible. Osgood engineers had observed that most steam shovel failures occurred at connection points where different materials joined together, so they designed machines with fewer joints and heavier individual components. Their boom assemblies used single cast-iron pieces, where competitors assembled multiple parts, eliminating potential failure points that could develop under repeated stress cycles. George Washington King, the Marion County native who served as one of Marion Steam Shovel's founding partners, embodied the practical American business philosophy that prioritized proven performance over theoretical sophistication. His local networking abilities helped establish relationships with railroad purchasing agents who had grown skeptical of European promises after experiencing field failures. King understood that American railroad construction demanded equipment that could operate reliably hundreds of miles from machine shops, making simplicity a competitive advantage rather than a design limitation. The engineering philosophy that united these American manufacturers represented a fundamental departure from European approaches to mechanical design. Where European engineers sought to optimize individual components for maximum theoretical performance, Americans focused on system-wide reliability that could withstand unpredictable operating conditions. Single-cylinder steam engines became the standard, not because they were more powerful than multi-cylinder alternatives, but because they had fewer precision surfaces that could wear out of specification. Basic cable and pulley systems dominated American designs, not because they were more efficient than complex linkages, but because they could be repaired by any railroad mechanic using standard tools. This philosophical divide extended to materials selection and manufacturing processes. European steam shovels showcased precision steel construction with carefully machined joints that demonstrated advanced manufacturing capabilities. American companies embraced cast iron components that were heavier and less sophisticated but could absorb impacts and thermal stress without failing catastrophically. Where European manufacturers prided themselves on tight tolerances that maximized mechanical efficiency, Americans deliberately built in larger clearances that allowed continued operation even as components wore during normal use. The practical advantages of American design philosophy became increasingly apparent as railroad construction expanded into more challenging environments. The Denver and Rio Grande Railroad's narrow-gauge construction through Colorado's Rocky Mountains in 1881 provided the ultimate test of steam shovel reliability. European machines, designed for the relatively stable conditions of European construction sites, suffered complete system failures when exposed to the extreme temperature variations and high-altitude conditions of mountain construction. Multi-cylinder engines lost power at altitude because their complex governor systems could not compensate for reduced air density. Precision linkages bound up when thermal expansion exceeded the tight tolerances that European engineers had considered essential for proper operation. American steam shovels not only survived these extreme conditions, but actually performed better than their manufacturers had anticipated. Single-cylinder engines maintained consistent power output at altitude because their simpler governor systems could accommodate air density variations without losing regulation. Cast iron construction proved ideally suited to the dramatic temperature swings of mountain construction, expanding and contracting without developing the stress cracks that plagued precision steel assemblies. Most importantly, when repairs were needed, railroad crews could perform maintenance using basic blacksmith tools, rather than requiring specialized equipment that was impossible to transport to remote construction sites. By 1885, American steam shovel manufacturers had captured over 90% of the domestic market while beginning to export equipment to construction projects worldwide. The success attracted additional companies to enter the field, each contributing innovations that reinforced the American engineering philosophy. The Barnhart brothers of Berea, Ohio, developed improved bucket designs that could handle rocky soil conditions that destroyed European excavators. Their reinforced cutting edges used high-carbon steel that maintained sharpness through thousands of digging cycles, while remaining simple enough for field repair when damage occurred. The dominance of American steam shovels reflected broader changes in American industrial culture that prioritized practical effectiveness over theoretical sophistication. Railroad construction crews, who operated equipment under conditions that would have been inconceivable to European engineers, became the ultimate arbiters of design success. Their preferences drove manufacturers toward increasingly robust construction that could withstand abuse while maintaining consistent performance. Equipment that looked crude compared to European precision instruments proved superior in the only metric that mattered: the ability to move earth. Reliably, day after day, under any conditions American construction projects could present. The transformation established manufacturing centers throughout Ohio that would dominate earth-moving equipment production for the next century. Marion, Bucyrus, and surrounding communities developed concentrations of skilled workers, specialized suppliers, and engineering expertise that created self-reinforcing advantages over competitors. European manufacturers found themselves unable to compete not just because their designs were less reliable, but because American companies had developed entire industrial ecosystems optimized for producing robust construction equipment that could operate successfully in the harsh conditions of American infrastructure development. The lessons learned during this period would guide American industrial development through the coming decades, establishing principles that would later influence everything from agricultural machinery to automotive manufacturing. Simplicity, reliability, and serviceability became hallmarks of American engineering that distinguished domestic products from their more sophisticated but less practical European counterparts. The Manchester Ship Canal project, announced in 1885, represented the most ambitious earth-moving challenge in European history and provided European manufacturers with the perfect opportunity to reclaim their reputation from American competitors. The proposed canal would stretch 36 miles from Manchester to the Mersey estuary, requiring the excavation of 54 million cubic yards of earth through some of England's most challenging terrain. British engineers promoted the project as a demonstration of European engineering superiority that would expose American steam shovel designs as inadequate for sophisticated construction work. European manufacturers approached the Manchester project with renewed confidence, having spent the previous decade developing advanced excavators specifically designed to overcome the reliability problems that had plagued their earlier machines in American markets. German company Menck and Hambrock introduced steam shovels with improved multi-cylinder engines, featuring redundant governor systems that could maintain power regulation, even if primary control mechanisms failed. British firm Ruston Proctor developed precision linkage assemblies with sealed bearing surfaces designed to resist moisture infiltration that had caused seizures in earlier models. The technical specifications of these new European machines represented genuine engineering achievements that surpassed their American counterparts in theoretical performance. Karlsruhe's 1887 excavator featured a four-cylinder steam engine that delivered 30% more power than comparable single-cylinder American designs, while maintaining smooth operation through sophisticated pressure regulation systems. The machine's articulated boom assembly could position its 2 cubic yard bucket with precision that allowed delicate excavation around existing structures, a capability that American cable-operated systems could not match. French manufacturer Couillet introduced rotating superstructures that allowed full 360-degree swing operation, eliminating the need to reposition entire machines when working in confined areas. Their advanced transmission systems provided variable speed control that operators could adjust for different soil conditions, optimizing excavation rates in ways that fixed-ratio American cable systems could not accommodate. Most impressively, these European machines incorporated steam-powered track propulsion that allowed self-positioning without requiring external locomotive assistance. The Manchester Ship Canal Company's engineering committee, composed of Britain's most respected civil engineers, evaluated competing steam shovel designs during extensive trials in 1887. European excavators consistently outperformed American machines in controlled demonstrations, excavating with precision and speed that impressed observers accustomed to European engineering standards. The sophisticated governor systems maintained consistent power output regardless of load variations. Complex linkage assemblies positioned buckets with accuracy that allowed excavation to within inches of specified dimensions. Thomas Walker, the project's primary contractor, initially placed orders exclusively with European manufacturers based on their superior performance during controlled trials. The decision seemed vindicated during the project's first months, as European excavators maintained excavation rates that exceeded contract specifications. Multi-cylinder engines provided smooth power delivery that translated into consistent digging cycles. Precision linkage systems allowed operators to work efficiently in the confined spaces created by the canal's narrow width and steep sides. The brutal English winter of 1887 proved more severe than European engineers had anticipated when designing their sophisticated machines. November brought persistent rain that turned excavation sites into quagmires of adhesive clay that clogged precision mechanisms and infiltrated sealed bearing surfaces. December temperatures plummeted below freezing for extended periods, creating conditions that tested every aspect of steam shovel design. European manufacturers had expected their home field advantage and familiarity with local climate conditions would provide decisive benefits over American competitors. Instead, the harsh weather exposed fundamental vulnerabilities in European design philosophy that their engineers had failed to anticipate. Multi-cylinder engines with their complex internal passages and precision-machined governor systems proved catastrophically vulnerable to moisture infiltration and freezing. Water that entered steam lines during wet weather froze, solid when temperatures dropped, blocking steam flow and causing complete power loss. Precision governor weights seized when ice formed in their bearing surfaces, eliminating the power regulation that operators depended on for consistent excavation performance. The sophisticated linkage assemblies that had impressed observers during controlled trials became liabilities under actual construction conditions. Sealed bearings that were designed to exclude moisture failed when subjected to the combination of adhesive clay and repeated freeze-thaw cycles that characterized Manchester's winter weather. Precision machine joints that had operated smoothly during demonstrations developed excessive play as wear accumulated under harsh operating conditions. Most critically, the complex transmission systems that provided variable speed control required frequent adjustment by skilled technicians who were not available at remote excavation sites. By January of 1888, European steam shovels were suffering failure rates that threatened the entire project schedule. Ruston Proctor's advanced excavators sat idle for days at a time, while crews attempted repairs that required replacement parts to be shipped from distant manufacturing facilities. Menck and Hambrock's redundant governor systems proved ineffective because both primary and backup mechanisms were vulnerable to the same environmental conditions that had caused the original failures. Carl Schutte's powerful four-cylinder engines became useless when precision steam regulation systems froze solid during extended cold periods. Thomas Walker faced the humiliating prospect of falling months behind schedule on Britain's most prestigious construction project due to equipment failures that had occurred under the supposedly ideal conditions of European home territory. The Manchester Ship Canal Company's board of directors, composed of prominent British industrialists and civic leaders, watched in dismay as their showcase project demonstrated European engineering inadequacy rather than the anticipated superiority over American methods. European engineering publications struggled to explain how their most advanced steam shovel designs could fail so completely under conditions that were less extreme than those routinely encountered on American construction sites. Technical journals published lengthy analyses attempting to attribute the failures to unusually severe weather conditions or operator error, but the evidence clearly demonstrated fundamental design flaws that had been masked during controlled demonstrations. The sophisticated systems that European engineers had promoted as superior to American simplicity proved unable to function reliably under the harsh but predictable conditions of actual construction work. The Manchester project failures represented more than just mechanical breakdowns. They symbolized the collapse of European confidence in precision engineering approaches that prioritize theoretical sophistication over practical reliability. Critics who had dismissed American steam shovels as crude farmer engineering found themselves confronting the uncomfortable reality that sophisticated complexity could become a fatal weakness when machines needed to operate reliably under challenging conditions that could not be controlled or predicted. Thomas Walker's desperate cable to Marion Steam Shovel Company in March of 1888 marked a pivotal moment in industrial history. Facing the collapse of Europe's most prestigious construction project, the Manchester Ship Canal contractor swallowed his pride and requested immediate shipment of American steam shovels to salvage the excavation schedule. The cable represented an unprecedented admission that European engineering sophistication had failed catastrophically under conditions that American machines were designed to handle routinely. Marion's response demonstrated the confidence that came from years of proving their equipment under harsh American construction conditions. Henry Barnhart personally supervised the preparation of 6 steam shovels for Atlantic shipment, selecting machines that incorporated his latest innovations in cast iron construction and simplified steam systems. These excavators featured single-cylinder engines with bore diameters of 14 inches and stroke lengths of 18 inches, generating consistent power output through steam regulation systems that had been tested through hundreds of freeze-thaw cycles on American railroad construction sites. The arrival of American steam shovels at Manchester in April 1888 created immediate controversy among British engineering circles. European observers expected the crude-looking American machines to fail even more dramatically than their sophisticated domestic counterparts, providing final proof that precision engineering represented the only viable approach to complex construction challenges. The Marion excavators appeared almost primitive compared to the failed European machines, with their basic cable and pulley systems and heavy cast iron construction that seemed to belong in a blacksmith shop rather than a modern construction project. The contrast became apparent within days of the American machines beginning operation. Marion steam shovels handled the adhesive clay conditions that had destroyed European precision mechanisms, without experiencing the binding and seizure problems that had plagued sophisticated linkage systems. Single-cylinder engines maintained consistent power output despite moisture infiltration that would have disabled multi-cylinder European designs. Most importantly, when minor repairs were needed, British crews could perform maintenance using standard tools and techniques rather than requiring specialized equipment and factory-trained technicians. The reliability advantage that had made American steam shovels dominant in railroad construction proved equally decisive in the challenging conditions of canal excavation. Cast iron boom assemblies withstood the repeated stress cycles of constant digging without developing the stress cracks that had plagued precision steel European assemblies. Basic cable systems continued operating smoothly even when contaminated with the adhesive clay that bound up sealed bearing surfaces in sophisticated European linkage mechanisms. Steam regulation systems that relied on simple mechanical governors, rather than precision machined components, maintained consistent performance despite the moisture and temperature variations that had disabled European power control systems. British construction crews, initially skeptical of American engineering approaches, became converts after witnessing the stark performance differences between American and European equipment. Marion excavators operated consistently through weather conditions that left European machines idle for repairs. The American machine's ability to continue working during light rain and moderate cold meant that excavation schedules could be maintained despite England's unpredictable weather patterns. Most significantly, when mechanical problems did occur, repairs could be completed quickly using readily available materials rather than requiring custom parts shipped from distant factories. The Manchester Ship Canal project's completion in 1894 provided definitive validation of American steam shovel superiority. Marion and Bucyrus excavators had moved the majority of the project's 54 million cubic yards of earth, while European machines contributed relatively little to the final excavation totals. The American equipment not only proved more reliable, but also more economical to operate, requiring less maintenance and consuming less fuel than their theoretically superior European counterparts. The success at Manchester opened international markets to American steam shovel manufacturers, just as an even more challenging project was beginning on the other side of the Atlantic. The French Panama Canal effort, which had begun in 1881 under Ferdinand de Lesseps, had collapsed in 1889 due to engineering challenges that exceeded European capabilities. When the United States acquired the canal rights in 1903, American engineers faced the task of excavating 260 million cubic yards of earth through terrain that had defeated French engineering expertise. The Panama Canal excavation became the ultimate demonstration of American steam shovel capabilities. 24 Marion excavators, operating under conditions that would have been impossible for European precision equipment, moved Earth at unprecedented rates through the challenging tropical environment. The humid climate that would have caused constant moisture infiltration problems in sophisticated European machines had minimal impact on robust American designs. Temperature. Variations that would have caused binding in precision assemblies were absorbed by cast iron construction designed with generous tolerances. The scale of American steam shovel success at Panama dwarfed even the Manchester achievement. Marion machines operating in Culebra Cut, the canal's most challenging excavation section, removed over 150 million cubic yards of rock and clay under conditions that no European equipment could have withstood. Single-cylinder engines maintained consistent power output despite tropical humidity that would have disabled precision governor systems. Basic cable systems continued operating reliably even when contaminated with the abrasive volcanic soil that wore away precision machined surfaces in European equipment. The vindication extended far beyond mere commercial success to represent a fundamental shift in global engineering philosophy. American approaches that had been dismissed as crude and primitive proved superior to European sophistication under the harsh conditions that characterized major construction projects. The principles that Henry Barnhart had pioneered in Ohio railroad construction, simplicity, reliability, and serviceability, became the foundation for American industrial dominance that would extend through the 20th century. By 1900, the transformation was complete. American steam shovel manufacturers dominated global markets not through theoretical sophistication, but through proven reliability under conditions that sophisticated European designs could not handle. Marion Steam Shovel Company had become the world's leading earth-moving equipment manufacturer by embracing engineering principles that prioritized practical effectiveness over impressive complexity. The lesson resonated throughout American industry. In engineering, as in life, elegance often lies not in sophistication, but in robust simplicity that works reliably under any conditions, every day, for decades. The 40-year journey from patent expiration to global dominance had proven that American engineering philosophy, rooted in practical experience rather than theoretical sophistication, could triumph over established European approaches when tested under the harsh conditions of actual construction work. The steam shovels that had been dismissed as farmer engineering had become the tools that built the modern industrial world,